Hello folks, as of next week we'll be learning about circular motion, uniform circular motion. In this motion we'll be learning about constant velocities and change of directions. This is the motion we feel when a car is rotating around the road. We feel a push outward. This is due to this circular motion. It's not always uniform, but we'll be learning only uniform part of it. So uniform circular motion. Today we'll be learning about simple initial values in there, definition of the values. Solve a simple question, and I'm going to ask you some simple questions to learn what is there for circular motion. So simply, if we have an object, I'm going to use my keys for that, and we rotate it, we will have a circular motion. If I can maintain more or less constant velocity here, it will be a uniform circular motion. This is another way, we'll be learning all these later on, of making a uniform circular motion. So what we have for a uniform circular motion, that an object is rotating around the circle, of course, and there will be, first definition, we will have the radius of the circle. So there will be a circle, the object is rotating around, let's say it was my keys and I'm rotating it. We will have an object in generally. There will be a velocity along this circle. So as the object rotates along the circle, we'll have always a velocity that is tangent to circle, what we call linear velocity. As in kinematics, and as we will learn so far, the value of it, the unit of it is meters per second squared. The linear velocity is the velocity along the line of circle. Change of distance per unit time along the surface, as we describe it in the first few lectures. We will also have an angular velocity here. As the object rotates along the circle, we draw this as well, so we have one here. It will also be going around angles. So we call theta, and the velocity traveling the angles we'll call omega, which is the angular velocity. So the linear velocity rotates along the circle, along x, let's say, and angular velocity rotates the angle. It travels the angle. The distance traveled for angular velocity is the angle. So W omega will be angular velocity here. And we'll define it as the angle traveled per unit time. And we'll take the angle as radian. So as you know, 2 pi radian is equal to 360 degrees. And if we have a full circle, the full circle has 360 degrees. One line has 180 degrees. If you look at the full angle in one line, and this is equal to pi. Pi is being the radian. And angular velocity is the angle traveled per second in radian. So the unit for angular velocity will be radian per second. We will also have acceleration. Now the first question that comes to our mind is, we have uniform circular motions. Uniform means the velocity, angular velocity, and the linear velocity is constant. Why do we have the acceleration? So we have acceleration. And the unit is meters per second squared as before. The reason we have acceleration is that although the value of velocity is constant, velocity is a vector, and as you can see here, the direction of the velocity always changes. And the reason for this change is that there is an acceleration always towards the center A, and causing this velocity to change throughout the motion in direction, not in magnitude. So magnitude is the same always, but the direction is changing because of that we have an acceleration. And if we have an acceleration, We'll have a force that is equal to m times a in the same direction as acceleration towards the center, which we will call centripetal force. Run out of colors. So towards the center as well, we will have centripetal force. So here, the force we have is Fc. It is equal to ma. Centripetal force. Now, what else we have? We have linear velocity, angular velocity, acceleration, and centripetal force. We also have frequency and period in this motion that we have to define. Frequency, we'll use the symbol F to show it, is the number of rotation per unit time. Again, the frequency is the number of rotation per unit time. And the unit of it is 1/second, or second to -1, and this is called hertz. So again, the frequency of the object, when it's rotating, there will be number of rotations per second time, and we can easily find it by just looking at the time and see how many rotations we have per unit time. And it will be the frequency. Again, the unit is second to -1. And the time it takes for an object to have one rotation is called period. So the period is, we'll use the symbol a large T for period, so we won't be confusing with time that we used small t before, and is the time it takes for one full rotation, and the unit is seconds. From here, we get our first equation that the period is equal to 1/frequency. Period and frequency are opposite to each other. Or, vice versa, frequency is equal to 1/period. So this is our first initial equation to know here. We have velocity, angular velocity, centripetal force, acceleration. We'll have the radius of the motion, distance between center to the point where we have the rotation along the circle. And we have frequency, the rotation per unit time, how many rotations in 1 second is my frequency, and period as the time it takes for one full rotation to finish. Now we have constant velocity. Constant speed would be better, and a better word to use here, because the direction of velocity is changing, the value is not. We have constant angular velocity. We are going to derive simple equations to find the equations for angular velocity, and from there we're going to move to A and F, centripetal force. Let me delete these. Leave the figure and do these simple derivations. So we have FC, we're going to find equations for all these. We have A, we have period is equal to 1/F, or F is equal to 1/T. We learned. Now we have constant velocity. For constant velocity, from kinematics, we had a very simple equation as x is equal to v times t. This is applicable here too. For linear velocity, let's look at linear velocity first. If we look at one full rotation, the object starts here, let's say in this position, rotates once, comes back in here. The distance it traveled is the circumference of the circle, and it's equal to 2 pi r. This is my x for one full rotation. And the time it takes for one full rotation is equal to period, as we described. The time it takes for one full rotation is described as period. Now if I apply these to here in this equation, x is equal to vt, I'll replace x by 2 pi r and t pi period, so I'll have 2 pi r is equal to velocity, linear velocity times period. And from here I can find an equation defining linear velocity as 2 pi r divided by t. This is one important equation in here. If you look at the units, we'll be using, as always, meters per second as for velocity. For time period will be seconds, for r will be in meters, and 2 pi will be entered as a number. So this is for linear velocity. Let's on this side look at the angular velocity. And we're going to use the same equation. X is equal to vt, let's say. We'll be replacing the velocity now with angular velocity. And this angular velocity just throws angles in here. So we'll be replacing x with the angle traveled. If we start again with one position and travel, after one full rotation, the total angle traveled by the angular velocity is equal to 2 pi in here, full angles. So after one full rotation, we'll have 2 pi traveled. After one full rotation, let's say. And here as well, we'll do one full rotation. So again, we have one full rotation and time is equal to period, so t is equal to large t. Entering all these values, w, omega for v, 2 pi for x, and large t for time, we will have 2 pi is equal to omega times period. And from here, I can define the value of omega as 2 pi over t. So we see here, v is equal to 2 pi over t times r, and omega is equal to 2 pi over t. Immediately what to see is that this value here is equal to omega. So for v, the linear velocity, I can also write down, let me put it in here, v is equal to omega times r. Now depending on the questions we're dealing with, to solve for omega, angular velocity, we can use this. To solve for v, we can use 2 pi over t r, or if we already know omega times r will give us our linear velocity. There is also derivation for a, but I'm not going to show it. It's rather lengthy, and I don't want you to go through that. But let me put it in here, since I'm moving towards left, let's move on left. Looking at force and acceleration, we will have acceleration is equal to v squared over r, and since force will be equal to m times a, it's equal to m v squared over r. So we have for acceleration, and this acceleration is quite often called also centripetal acceleration. Let me put it in here as well. Let's say AC to identify. You may also put A, but generally in the books and the questions, you'll be seeing it as centripetal acceleration. So our force, let me rewrite this, is equal to m v squared over r. And our acceleration is equal to v squared over r. Force, Fc, nice word, will be again Newton. V is meters per second squared, meters per second. R is meters and m is kilogram. As you might have already noticed, the Newton is equal to kilogram meters per second squared always. So here are our values. We have linear velocity is equal to 2 pi over t times r, or omega times r. Angular velocity equals to 2 pi over t. We have AC, centripetal acceleration, equals to v squared over r. And we have FC, mv squared over r, coming from am times centripetal acceleration, AC. Here are the definitions, and let's solve the question. I'm looking at the time, I don't want to make this very long and boring again. Let's solve a simple question. This is a very nice question, applying this motion to life, so I'm going to solve it here for you. I'm going to drop the vector signs. I already did drop the vector signs for velocity and force. We're looking at the magnitudes. And again, as we did in the Newton's law section, we'll be defining the directions, and after we define the direction, we'll be just looking at the magnitudes. So let me find my question and read it to you. The vacuum cleaner takes the air inside by use of uniform circular motion, rotates and takes the air inside. Let's say the motor has a radius of r 10 centimeters. Let me try to draw a vacuum cleaner. Let's say this is a vacuum cleaner. We're cleaning. There's a motor inside that taking the dirt inside by just taking the air. So rotating, having a uniform circular motion. And it has a radius of 10 centimeters. R is equal to 10 centimeters. It has 600 rotations per minute. So the vacuum cleaner has 600 rotations per minute. And the question is asking me calculate frequency F, period T, angular velocity, linear velocity, and AC, acceleration. Let me draw this in here separately and larger. So we have R is equal to 10 centimeters. 600 rotation per minute would be frequency, but we're not going to convert this to rotation per second, so we'll have frequency in correct unit, in hertz. 600 rotation per minute is actually equal to frequency. I'm going to convert this to rotation per second. 1 minute is equal to 60 seconds, so 1 minute. Convert to 60 to multiply by 60 will be equal to 60 seconds. This is my conversion here. And then this will be rotation per second. Will be giving me F as second to minus 1 or hertz. So 600 divided by 60 is 10. F is equal to 10 second to minus 1 or hertz is the units. This is my frequency. I calculated it. If I know frequency, I can get to T easily because T, the period, is equal to 1 over F, 1 over 10, 0.1 second. So 0.1 second, we have 1 full rotation for the vacuum cleaner. So I know F and I know T. Let's go to W. W is equal to 2 pi over T. T is 0.5. 2.1 second divided by 0.1 second. And W should be equal to 6. No, sorry. Oh, we don't have it here actually. Let me solve it. Let me solve 2 times pi. Where's my pi? Pi. I'm sure I have it here. Okay, interesting. Sorry about that. Pi divided by 0.1. 62.8 radian per second will be my answer. Now let's move on to V. I want to calculate V using, let me divide this part 2 pi over t times r squared. We know 2 pi over t already. We can enter this in here. And r squared, so 2 pi over t times r. And r is in centimeters. I'm going to convert it to meters to get the velocity in meters per second. There's an optional answer. I can get velocity as centimeters per second, depending on question. It could be okay or not. But I'm going to find it in meters per second because we have stuck with MKS students, and I want to do the same in here. So I'm going to convert r in here first of all. R is equal to 10 centimeters. I know 1 meter is equal to 100 centimeters. So if I divide this by 100, I'll get 2 meters. R is equal to 10 centimeters times 1 meter over 100 centimeters. Let's do this correctly, exactly. So R is equal to 0.1 meters. Enter in here, 2 pi over t times r. Let's put the values actually. 0.1 second times 0.1, we'll get the answer as 6.28, about 6.3 meters per second. And now we have everything. Can we get A? Yes, because to get A, we have an equation. Let's define this so it won't be too messy in here. AC is equal to V squared over R. So all I have to do is square this and divide by R again. 6.3 meters per second squared divided by 0.1 meters. Let me see if I have an answer for that. 394.8 meters per second squared. So it's a very large acceleration. The rotation is very fast, so it's taking all these dirt from our house by doing that. And from here, it's not asked in the question, but it's pretty simple to find F is equal to ma. It's not asked because mass is not given. But centripetal force is m v squared over r, which is mac, can easily be also found. Let's actually find it. What would be the mass for this motor in here? Let's take mass to be 1 kilogram. But it will be too easy. Let's make 2 kilograms. Let's take the mass to be 2 kilograms. We can easily solve for FC, centripetal force, which is equal to 2 kilograms times acceleration 394.8 meters per second squared. And the answer is just 2 times that. I don't have it here because I didn't do it before, but let's solve it. 394.8 789.6 newtons. So FC is equal to 789.6 newtons. So this is what we need to deal with in different situations. So we will be having different types of motions as I've shown before. We will be dealing with cars rotating around the road that is flat. We will be dealing with cars rotating around the road that has an angle. There are more complicated situations. But generally what we will be dealing with is either period, frequency, velocity, or angular velocity. Some will be given, some will be we'll be needing to calculate. That is the general idea. Now I'm going to delete this, and I think I'll solve one more question involving the simplest case of the applications of uniform circular motion. And I'll move on to more complicated cases in the next lecture. So applications. And the first one we're going to look at the horizontal uniform circular motion. or let's call it horizontal. If we are dealing with horizontal uniform circular motion, we could be dealing with a car that is rotating around a circular road that is flat, no angles, or we could be dealing with an object that is rotating along horizontal only, like the one I rotated along my head. So we don't have to deal with the acceleration due to gravity in here. Let me try to draw it for you. I'll solve one question and I'll put a question and one catalyst to solve in the classroom. We'll be dealing with these directly through questions, but what we have generally, if we have a motion along the surface and along the horizontal, let's say the person is rotating an object along horizontal, let's say you're doing it on a table. So you don't have to worry about mass and the gravitational force because it's either equalized by the table if you're on the table, or if you're in the air, rotating an airplane, let's say, the airlift will be dealing with the mg, the gravitational force. So you don't have to deal with it in these type of horizontal uniform circular motion cases. What we will have is a mass in here. We'll have r, and we're rotating, so we'll have our linear velocity. Angular velocity is always there, of course. Rotating an angle, period, frequency already there. And we'll be dealing with, for example, what is the tension on the rope. Interesting thing about circular motion is that although we said the acceleration AC, thus the FC, centripetal force is towards the center, how the objects feel this force will always be outside of the center. So from now on, after this question, we'll be showing centripetal force outside of the center. This is very non-intuitive in real life. That's how we feel it. If we are in a car and the car is going in this direction, rotating, we feel a push outward. This is what we feel. It's like a feeling motion, the reaction force, not the action. So for example, if we jump from something down, as we hit the floor, actually we apply a force to the floor that is equal to mg, our weight. The force is exerted on us. But what we feel is an upward force that is pushing us and hurting our feet. That's what we feel here too. So as not to confuse ourselves, we'll always be showing the centripetal force outside to calculate values. So if I have a rope rotating an object along the rope, the string will be pulled by tension, and centripetal force will be pushing the object outside. And we actually, if we rotate, we actually feel that push. This is the force that we feel. Exactly, we can feel that pulling outside. So if I rotate this horizontally, I have string pulling me inside on the object and FC pushing the object outside. If these are in equilibrium, then FC pushing outside will be equal to the tension force along the string pulling the object inside. And using this equilibrium, we can find value of tension and so on. So let's move on to an example and understand this better through an example. There is a kid playing with an airplane, rotating the airplane along horizontal axis. Like this one, let me use this actual figure. So a boy playing with an airplane, rotating it along a rope. Let me read the question for you. The model airplane with a mass of 0.9 kilograms, so the mass is equal to 0.9 kilogram, in figure moves at a constant speed on a circle that is parallel to the ground. So it's a horizontal circular motion. The weight of the plane is balanced by the lift by its wings, so there's mass mg, the force pulling down the airplane for sure, but it's balanced by the airlift, so we don't care about that. We are looking at horizontal only. Find the tension in the string if its length is 17 meters. So the length of the string, which is r in here, 17 meters. That's a long road. And the speed of the airplane, so we also know we know R, 17 meters. We also know the linear speed. The speed of the airplane is 38 meters per second. So find the tension if the speed is 38 meters per second and length of the rope is 17 meters. Again, what we're going to do is we feel the centripetal force as a push outward, and we feel the tension push inward. If the system is in equilibrium, if the rope is not breaking, or the object is not accelerating in this direction, which is not happening, then we're in equilibrium. So we have an equilibrium situation in here. Only the motion is slightly different, and Newton's law still applies. Total forces are 0, so forces pulling the one side to the right will be equal to forces pulling the other side. So I will directly write down here Fc is equal to T, because we know where we come here from. We have the F total is equal to 0, and then it will be chosen one direction as positive. Let's choose this as positive, this is negative. And then we'll say Fc minus T is equal to 0, Fc is equal to T. But I believe and hope that we are comfortable enough now to directly jump in here saying that system is in equilibrium, total forces are 0, so forces pushing to the right are equal to forces pushing to the right. What we have force pushing to the right is Fc only, and it's equal to T. So if I find Fc, I have T. Quite simple. So T is equal to Fc. And I use my equation as mv squared over r. I know mv and r, I can get Fc easily. So T is equal to Fc is equal to my mass of 0.9 kilogram. V is 38 meters per second, so I'll square that. 38 meters per second squared divided by r, 17 meters. This is quite illogical. We cannot rotate a 17 meters rope, but it's okay. It's good for the sake of learning. And the answer should be 76.4 Newton. Again, please read the solutions for practice and tell me if I'm right. If I have any error in the answers, I can change it. I'll put some questions, simple questions for a start for circular motion as pre-lab, and see you on Monday. Have a nice weekend.